Welcome to the Insightful Professor. Today we begin an examination of multi-table operations. There are many such operations that are supported in the language of SQL. What we're going to focus on in this particular video is a type of a join operation referred to as the inner join. First, let's give you the idea of why we're getting into multi-table operations. Well, SQL supports a variety of operations as we see here on the screen. Different flavors of join, different types of subqueries, different types of set operations. But the motivation behind these is that sometimes when you need the answer to a question from the data stored within a database, the entire answer cannot be obtained by going to just a single table. This is because databases capture relationships. And when we design a database, we tend to put information about one kind of thing and one kind of thing only within a particular table. If rows in one table relate to rows in another table, then we express that relationship in some way, and then we can access the multiple tables together. So the techniques that we have are referred to as join, where we have inner join, outer join, and another type called a cross join. We have subquery, which could be what would be called non-correlated. And when people often refer to subquery and don't specify the variety of subquery, it's probably such that they're thinking about a non-correlated subquery. We also have, in contrast to that, something called a correlated subquery, and then another way of using a subquery called a table expression. For set operations, we have union, an intersection operation, and some kind of a set difference. Now, the subquery and set operations will postpone to another video. In fact, we'll also postpone our discussion of outer join until we get to another video. Now, the nature of relational databases is such that each table is a representation of information about just one particular type of object, such as a department, employee, or part. And again, the reason we're doing multi-table operations is sometimes we need to get a little bit from one table, a little bit from another table, maybe even a third table, bring that together to assemble a complete answer. So in order to do this, in any of these forms of multi-table operations, we'll see that we'll be extending the select statement by adding some additional syntax to support these various operations. Now, a word of warning before we get into all of this. The complexity of multi-table operations really does not seem to lie within the syntax, that is, how you formulate the statement, how you write the query, but it's more along the lines of the data semantics. So multi-table operations are more complex than single-table operations, due not so much to the syntax as it is attributed to the semantics. So the idea is that the user formulating such a query has to be familiar with the nature of the data stored in each of the tables in the database and has to understand how to relate data from one table to data in another table, and also recognize the idea that the data in one table, when matched to data in another table, will produce a single match or may produce multiple matches. This is part of, again, understanding the semantics of the relationships that exist and have been captured within the database. So, if you don't understand the semantics, you're going to be at a real loss or real disadvantage. The problem here is that you could be asking the wrong question. You get the right answer to the question you asked, but because you didn't really understand the relationships, you asked the wrong question. You don't get a pat on the back for doing that. So you really want to make sure you're asking the right questions of the database, which requires an understanding of the data content, the relationships, the business rules, hence the semantics of the database. So what we start with here is the join operation. And the join operation is such that what we're looking at is we'll be writing a single select statement, but the select statement will be making reference to columns in more than one table and will be directly making a reference to more than one table. What happens is we have to express the association or the relationship between the tables by specifying some kind of a join condition. Now, the way I like to explain join to folks is from a conceptual point of view. It is the joining of two tables is really concatenating rows from the two tables. You take a row from one table and you kind of append to it a row from another table. And when you put all of that together, now you've exploited this condition that exists between the two different sets of data, and you've brought together something that is meaningful. So the result of the join operation is going to be a table. Just like any select statement that we've executed up to this point, whether it be against a single table or whether it be against multiple tables, the result of a select is always a new table, what we'll call the result table. So that result table contains rows and columns. So the result of the join operation is also a table. And this table has a row for each match which occurred between the two tables that participated in the join operation. And because the join is being performed here as a data retrieval operation, a read operation, or a select operation, the original tables that participated are not affected in any way. Their content would not be altered. They're simply two sources of input to the join operation. In practice, there's no limit to the number of tables that can be brought together through a series of join operations. Strictly speaking, a join can only be performed against two tables, but there's nothing to say that once we join two tables and produce that new intermediate result table, that intermediate result table could not be joined with yet another table, a second join. And the result of that, again being a table, could then be joined with another table. So in theory, we could bring together as many tables as necessary to answer some business question. In introducing this video, we indicated that there were three categories of joins. There was an inner join, an outer join, and a cross join. Here we see an extended list. It turns out that according to the way you can formulate a join, according to the ANSI SQL standard, there's more than one way to express an inner join. Actually, there are a couple different ways, perhaps, that you could express an outer join. These are all syntactic differences. So as we look at Oracle database, what we see is, according to the ANSI SQL standard, all of these different varieties of join exist, and these are all supported by Oracle. If we were to flip over to another database, such as Microsoft SQL Server, we may see that most of these are supported. Again, it's going to depend upon which version or which release of a particular product that you might be dealing with. So what we're going to focus on here is going to be a subset of this. We're going to talk about comma-separated, cross-join, natural join, condition join, and also briefly an explicit syntax for the inner join, all within this video. We're not going to discuss column name join at all. I think it's kind of redundant. It's not necessary to look at that syntax. I haven't really seen it used much, if at all, in practice. And in a separate video, we'll discuss the outer join. So the primary difference between a majority of these types of join is just going to be the syntax. So let's look at the comma-separated join. Comma-separated join, you can pretty easily see where the name comes from. What we're going to do is, in the from clause, instead of listing a single table, we are going to list multiple tables, the two tables that are going to be joined. And we separate the names of the two tables with a comma, hence the name comma-separated join. This is actually standard SQL. This is an older syntax. Oracle has supported this effectively since day one of the product. Other vendors support this as well. And we'll also see another form called condition join that was added a little bit more recently in some of the products, and we'll discuss how that works as well. But let's focus on comma separated for the moment. So we list the two tables to be joined in the from clause, and we separate the names of the tables with a comma. In the select clause, we list the columns that we wish to be retrieved. Now, these columns can come from either of the two tables. We can also express a relationship within the query in the where clause. That's optional. I've enclosed that here in the square brackets to show that you don't need to have a where clause, although you probably are going to, because if you exclude a where clause, you'll produce something called the Cartesian product or the cross product, which generally is not going to be of much use to you. So here are a couple of examples where we do omit the where clause. Select all of the columns from the class table, all of the columns from the course table, and then list the two tables. We could also simply say select asterisk and not qualify the asterisk with the names of the columns, names of the tables if we wish. And these two queries then become equivalent to one another. But again, these two queries, if we were to run them, would produce a lot of data in the output, much of which is really not going to be of any meaning because you're taking a course and a class and appending the two rows together, but you haven't said that the class is a scheduled offering of a particular course. That's the idea of what the cross product is going to give you. It doesn't really bear down and look at the meaning of the data and follow a relationship. That being said, we're just kind of focusing on the syntax at this point, so let's move ahead and look at a little bit more of this. A more meaningful result can be achieved if we include the where clause to express what we call a join condition. The join condition is a relationship that we either know to exist within the database or we believe to exist or would like to exploit in some way within the query. It doesn't have to be defined to the database system itself. Here you would select the columns, the names of your tables, and then in the where clause, typically it's one column from a table, a column from the other table, and you express a relationship here using a relational operator. Very often that's going to be equality. So this is referred to here as an Equi-Join because the condition says that this column from table 1 has a value that must be equal to this column over here in table 2. So this equality condition is making this an Equi-Join. We don't have to use equality. We can use any relational operator, such as greater than, less than, not equal, whatever makes sense for our particular objective. So in this example, we're saying give all of the columns from the course table plus selected columns from the class table, and we express the two tables here, and then the where clause says how to relate them. The variation on this shown at the bottom of the slide says we're going to express the join condition, how to relate the tables, and then also add another condition that does not have anything to do directly with how the join is performed, but will get rid of extra or unwanted rows. This is referred to as a filter condition. So the where clause in the comma-separated syntax includes a condition that expresses a relationship or how to match the rows, and may include additional conditions which says how to get rid of the extra unwanted rows by using filters. So we have join condition and filter condition. Both of these would be expressed in the where clause using this syntax. Excuse me. Now, very often we're going to deal with tables that might have long names, and some of the column names might be common to the two tables. It's always good practice to qualify the column name with the name of the table from which you got the column. So back here we said, get me the section number from the class table. Get me the course instructor faculty number from the class table. And then down here in the where clause, we said, get me the course number from the course table and the class table's course number as well. Now, up here in the select clause, it wasn't absolutely necessary to qualify the columns because SEC is actually unique to the two tables. CIN, STR, FNO is unique between the tables, and so on. But here in the where clause, it was absolutely required because CNO, if you simply say select CNO, or where CNO is equal to CNO, that is ambiguous. It is necessary to say the CNO in the course table or the CNO in the class table, and you must qualify it in some way to identify which instance of CNO you're talking about when the column names are common. It's good practice to qualify all of the column names, but strictly speaking, it's not required. As an alternative to using the name of the table, on this slide we show that you can introduce an alias, a correlation name or correlation variable, or sometimes referred to as a table alias. This is beneficial because very often people that write the correlation names or correlation variables use something that's very short, much shorter than the name of the table. So here we have course has this alias for the duration of the query. This alias will not be understood or recognized by the system beyond the execution of this query. We've associated C, just an arbitrary name that we came up with course. We've associated L with class. And notice there's a space between the table name and the alias or correlation variable that we introduced. We then are able to use these correlation variables anywhere within the query to qualify the name of a column and avoid an ambiguous reference. Okay, that was intended as kind of a quick overview of concepts and syntax. What we now want to do is take a much closer look at a practical example. The examples that we just gave you with class and course were intended to give you a feel for how the join operation is expressed, focusing much more on the syntax than on the semantics. We wanted to give you that taste, and now we're going to slow things down and look very carefully at how a join actually works. And I think by using these two tables and the examples that we have in the next several pages, you'll get a good feel for what the join is, how to use it, and when it's going to be necessary. So here we're going to look at two tables, the staff table, which could be thought of as an employee table, and the department table, kind of an administrative table. We recognize in the real world that staff members are associated with the department such that an employee works in a department. So we assume that this relationship exists. I say that we assume this because in our particular database, there is no foreign key, there's no referential integrity to relate staff to department. We just perhaps have this understanding that a staff member is a type of employee, and a staff member, as a consequence of being an employee, works in some department. So based on that, we formulate a query here, which is a real neat little join. We're going to select all of the columns from the staff table, comma, the department table, but we're going to express this relationship that we believe to exist, where the staff member's department is equal to the department table's department. That is, we're looking for rows in a department table and rows in the staff table that have the same value in the DEPT column, and for those rows, we're going to perform the join, that concatenation that I was talking about. So both tables here are referenced in the from clause, and the table names, again, are separated by a comma because we're using the comma-separated syntax. The table names can be specified in any order. A lot of times people will ask, do I have to say staff first, then department? What happens if I go the other way? Well, when you select all of the columns, that's the only time it's going to make a difference in terms of the result. In terms of performance, it should not make a difference at all. So with that kind of background in mind, let's go ahead and take a closer look at just what's going on by going into the database and playing around with this. Okay, so here's my Oracle database, and I'll give some examples in SQL Server as well. So here's the query we want to look at. Select all of the columns from staff and department, where staff's department ID is equal to department's department ID. Now, before I do this, let's take a closer look at what's going on here. I'm going to select from the staff table. And if I do that, we see we get one row for each staff member or each employee. We get the name of the employee, the job title, the salary the employee earns, and the name of the department where the employee is assigned. The other table we're going to be looking at here is the department table. And what do we have in here? Well, we've got the name of the department, the building, and the room. That is location information, where a department resides, where it's located somewhere on campus. And then also information about the faculty member who chairs or is responsible for the department. Our first observation is that the DEPT column in staff looks a lot like the DEPT column in department. We might be lulled in to believing that it's a foreign key. However, observe that Euclid is assigned to math, Archimedes is assigned to engineering, and we don't have a math or engineering department. Recall that in the department table, DEPT is the primary key. So therefore, DEPT from staff could not be a foreign key because these two rows would be violating referential integrity. So coincidentally, we have a column with the same name in the two tables, but it is not formally recognized by the database system as being a foreign key. That's very important. There is no actual relationship between the rows in these two tables, yet that does not prevent us from doing a join. That's pretty neat. Now, let's take a closer look at what's going on here. Suppose you needed to contact the employee named Dick Nix. You said, I got to get a hold of him, I got to talk to him. So I know his name, I know his job title, his salary, I know which department he works in, but notice there's no real contact information. Nowhere within the data that we've recorded for the staff members do we have anything about where on campus this individual might be located. However, if we go to the department table, each row in the department table has associated with it a building and a room, some physical location on campus. The idea is if you have somebody who works in philosophy and you find the row for philosophy in the department table, you found the building and the room on campus where the philosophy department is located. You could go there and presumably find anyone who works in that department. And the same is true for any of these other departments, such as theology, or CIS, or management. The point is that the building and room really don't define the employee, they define the department. That's why these attributes were stored in the department table. What we would like to do is to be able to get the information about the employee together with the information about the department in a single row. If we were able to do that, then I could select where the name is, for example, Hank Kiss, go over here and get the building and the room. The only problem with that is such a row does not exist within the database. There's no table that contains information about the staff member together with information about the department. Okay, the only problem with this is there is no such row in the database anywhere that contains information about both the staff member and the department. So we can't really find the answer. Aha! Turns out we can't. We can make such a row. Remember, every query that you run against the table produces a new table. I reminded you of that at the start of the video, and I also pointed out that when we do a join, we're producing a new table. And I had said that the join was a concatenation of rows. Let's remove this, grab the query that we were just discussing, and take a closer look at this in action. Now, here we go. We have done exactly what I was hoping to do. We have the columns that describe the staff member, plus the columns that describe the department. We find the individual Hank Kiss, and in that row, we find the building and the room on campus where Hank Kiss's department is located, hence that's where Hank Kiss should be. So what we have here is a join. How did we achieve this? Well, we said give me all of the columns from staff and append to that all of the columns from department. that's where the order of the tables has an effect. So notice we have all of the columns from staff, and appended to that are all of the columns from department. If I had said select from department, comma, staff, then these columns for department would be over to the left, and the columns for staff would be appended over to the right. That would be the only difference here. There would be no difference in the content of the result. There would be no difference in the efficiency or the performance of the query as it was executed to produce that result. Now, what we did was we said, give me all of the columns. Okay, so notice there was a column that was common to the two tables, a column name, I should say, that was common to the two tables. So there are two columns called DEPT in the result, because we said, select asterisk, give me all of the columns. But we had also said, I'm interested in the rows from staff that have a value in the DEPT column, where we can find a value that is equal to that in any row in the department table DEPT column. That's the join condition. And observe in the result, for every row that we see, it's the same value in each of the two DEPT columns. That's exactly what we asked for. Now, the reason we had to qualify here was, once again, to avoid ambiguity. If we were to go out and say, give me all of the columns from staff, comma, department, where, and we simply say where DEPT is equal to DEPT, you might get an idea of what's going on, but the system says, it doesn't make any sense to me. It's ambiguous. And that's exactly what you see here. You get a similar type of error when you do this with SQL Server. It says, you got to tell me which table you want this DEPT from and which table you want this from. So every time there's a column name that appears multiple times, and you use that column in the where clause or the select clause, or you're retrieving it in some way or using it to guide the retrieval of the query, you have to qualify the name of the column. Otherwise, the reference is considered ambiguous, and the system responds by giving you an error. Now, that's the basic idea of the inner Equi-Join. Now, some of you probably looked at it very carefully and said, well, wait a minute. You only have 6 employees. A moment ago, I thought there were some other folks there. What happened to Euclid, Archimedes, and Da Vinci? And you also noted that there were 4 departments, but I only see 2 of them here. Well, that's a very good observation if you made that observation. Let's go back and take a closer look at what happened. Here's the staff table, and we said I'm looking for a row where this value, whatever it is, can be found in a row over here in this other column. And sure enough, theology is found here. So that would mean all 4 of these guys that work in theology should appear in the result. And let's see if that's the case. And we have all 4 of the people in theology. Okay, looks good. Then we've got these 2 guys from philosophy, and we note that there is a row for philosophy down here. And sure enough, the 2 folks from philosophy also appear in the result. But those are the only 6 employees. Why did the other 3 not appear? Well, we had Euclid, who was in math, Archimedes, who's in engineering, and Da Vinci, who is in, well, we don't know. It's the null value. And remember how null works. We talked about that in the missing information video. So we don't have a math, we don't have an engineering, and null is not going to be equal to any of these. That explains the absence of Euclid, Archimedes, and Da Vinci from the result table for the join. Okay, let's go a step further. What about CIS and management? These 2 departments are not reflected in the result of the join because, as you can see here, there is no CIS, there is no management. Same reason, but we're missing rows from the other table. So what you have in your result would be only the rows from the 2 tables that were able to satisfy the join condition, what I've been referring to as the quote-unquote match. Such a join is called an inner join. And this particular variety of join is called an inner Equi-Join. And it's an Equi-Join because the join condition was equality. And we got only the rows from the tables that found a matching row, that is, they satisfied the join condition with a row in the other table. So the inner join only shows you the rows that satisfy the join condition. And the join condition in our case was equality. So it's an Equi-Join. More formally, there's a big name to this particular example. This is an inner Equi-Join. This is probably one of the more common types of joins that you'll see. Okay, we've covered quite a bit there. Now, that was a simple Equi-Join. Here, I make a little change to the query, but I also add an important comment. I call this a practical Equi-Join. If you think about how tables are structured, very often a table will have many columns, 20 columns, 50 columns, 100 columns. But whenever you ask a query, you're probably going to be retrieving only a subset of the columns. Most of the columns in the table are not going to be needed to answer a particular question. And for that reason, you select a subset of the columns by just listing the columns that are meaningful and relevant to your particular question. Well, when you're selecting rows from two tables and you're doing a join, you're probably even less likely to say select asterisk, because you're going to have a huge number of columns, and most of them probably will not be relevant to answering a particular question. So therefore, what we're going to do is modify our join to pick only the columns that we need to see to answer a question, and then furthermore, only the rows by adding a filter condition. So in this particular query, we're refining our join and adding a subset of columns and a filter to target only the very specific rows that are meaningful for the particular query's answer. Go back to the database and grab this guy. Here was our original query. Here's the one we're about to run. An observation we can make before we run this is that, in essence, the join could be considered these two lines of code here. You're identifying the tables from which you're going to be getting the data, and you're identifying some condition or relationship between the rows in the two tables to perform the join or the concatenation of rows. So in essence, we could say these two lines that I'm currently highlighting could be thought of as achieving the join. That being the case, then this would be the join. And what do we have when we do the join? Well, just a little reminder. Let's take this, and if we do this as our join, what's the output? The output is a table. Now, given that this is a table, we can pick any of the rows, any of the columns. That is the idea of what we're looking at now from the standpoint of what I'm calling a practical Equi-Join. So what I'm going to do is I'm going to take from this table and pick only the e-name, the e-salary. It doesn't matter which department because they're both the same, but I pick one, and when I pick it, I have to qualify it. And then the building and the room. I pick a subset of columns. And then furthermore, with a filter condition, I pick only some of the rows. Those rows where the salary is greater than 1,000, so it'd be just these two guys here. So let's see if that's what happens. Perfect. So we got these two rows, but then we refined the columns by picking only a subset of columns. And you can compare the result we produced with what I've highlighted here. So this is what I call a practical Equi-Join, because we typically do not want all of the columns and probably not all of the rows either that materialize. Remember, we're dealing with very small tables here, 4 rows, 9 rows, 14 rows. That's nothing like what goes on in the real world. Now, to make it even more practical, we kind of turn it up a notch and go one step further here. What we're going to do is join rows from the course table with rows from the department table. The reason I say we're kind of turning it up a notch is that there's a parent-child relationship here. For each department, that department sponsors or is responsible for many courses. A given course is sponsored by, or the responsibility of, exactly one department. So we have a true relationship that exists here, and that relationship has been defined to the database. So referential integrity is in play. So we take the primary key of one of the tables, and we look for something being equal in the foreign key of the child table. And this will give us rows that kind of make sense. For any given department, we're going to get a list of the courses that are sponsored by that department by exploiting this relationship that is known to the database. Furthermore, we do a little filter and exclude some of the rows based upon lab fee. One final point is that we are producing a result table, and we can actually add to the query an order by to control the presentation of the result so that the rows come back sorted or in order in some way. So we're exploiting a relationship here that might be called courses offered by department. Information about relationships are part of the metadata in the system catalog. So you could actually query the metadata if you knew where to go, and you could actually find the name of the constraint and the names of the columns and so forth. That information is part of the metadata. Remember, the system needs that information to support things like referential integrity, but it turns out we can query that ourselves if we had some interest or desire in so doing. So let's go look at this in action. Okay, taking our example here, I'm going to grab the code and run it, and here we go. So what we have is course and department are brought together, and we're picking a couple columns from course, and we're picking a column from department. What might be a little bit more meaningful to confirm that this ran properly is let's take this query and do a little modification to it. I'm going to select the C department column and the DEPT column because those were the two columns used to form the join. I'm going to bring those into the output just so we can confirm that the query worked the way we hope it did. So when I run it, sure enough, we can see that the join condition that we expressed here was indeed satisfied, and those are the rows that come back. Now again, the reason there are such a small number, there are so few rows, is due to this filter here. The lab fee must be greater than 175. There are other rows from theology, other rows from philosophy, other rows from CIS, but the lab fees all fall short of this threshold of 175. So we've built up from the basic concept of a join to now where we're looking at something that seems quite practical, quite useful. Taking a step further. In this particular example, it's a little peculiar if you scan it real quick. What it says is select the e-name and e-title columns from the join of staff and department, and we've got a filter condition with a building as HU for humanities. It seems kind of odd because these two columns are coming from the staff table. So the question is, why am I selecting columns from the staff table, but I'm doing a join with department? Do I really need a join? Well, the reason you need to access the two tables together in some way, and here we've chosen to do that with a join, is based upon the filter condition. The filter condition is evaluating a column that is in the department table. Remember, there's nothing about location stored within the staff table. So if I wanted to identify all of the employees who work in a particular building, I could not go to the staff table alone to get that answer. It's necessary to bring staff and department together, and for those rows in that intermediate result, that join result, that have a building equal to humanities, it's from those rows that I then select the staff information. So again, this is an illustration of why it's so important to understand the data semantics. You need location information to correctly identify a particular set of staff members, but the location information does not reside within the staff table. So you have to understand what is stored in each table and then how to meaningfully and correctly relate the rows from the different tables to produce your result, from which you can then work and extract the actual answer that is of interest to you. Another thing we can do with a join, well, effectively anything you can do with a single table, you can do with a join. So again, think of the join as being from department, staff, where department DEPT is equal to staff DEPT. That produces the table we've been looking at with information about department and staff. And from that, I pick some of the rows by putting filter conditions. And I also get something from the rows in terms of a numeric value. What is this doing? This is giving me the total salary. Maybe it's budget type of information. Total salary for all of the employees who work in the humanities building, room 100. Remember, even though I'm looking at the salary column and applying an aggregate function, I can't do that against staff by itself to answer this question because the location information about building and room is not present in the staff table. So this is kind of a variation on the query we just looked at. I again am doing the join to relate the rows in a meaningful way and then applying a filter from columns that came from one of the tables and then using the columns that come from the other table to produce the result that I render for my user. The interesting twist about this one is I'm applying an aggregate operation, something that we saw in our query on aggregate operations. We saw that we could do that with a single table. Here we can do it with the result of a join. Because remember, in essence, it's these two lines here that are producing a brand new single table, even though the data comes from multiple sources. Take it a step further, and we can actually do a group by applying our two aggregate functions. And here we're grouping by the value in one column and doing the average of a numeric and the average of another numeric. The exciting thing about this example is lab fee originally resided in course, salary originally came from staff, but once we do the join, these two values are sitting side by side in rows in our result set for the join. We can then group all of the rows that have the same value in department and apply the aggregates. Finally, we throw an order by in there just for good measure to arrange the result in some meaningful way. But again, this is just an extension of operations that we've seen with a single table. We're simply applying these operations against the join that's being produced. Another thing that we looked at in earlier videos involving one table was the idea of doing things like arithmetic operations, taking one numeric column, divide by another, some kind of expressions. So we looked at a video on patterns and expressions. And here is an expression where you take a number divided by some other number. We also looked at pattern matching. In this case, say that employee name has to resemble this, has to begin with the letters MA, and they can have anything that follows. Well, those were operations we saw applied against a single table, and what we're doing here is producing a single table as the result of joining staff and course based on this condition. And again, remember, there's no official relationship here, so we're just saying, use this condition that I'm telling you about. It's not something you'll find within the database that's enforced there, but that doesn't prevent me from doing this. Then once I've done the join, I pick the columns I want, do the arithmetic, do the filtering using pattern matching, and then look at the order by. The order by is doing a primary and secondary ordering. And what's interesting about this is e-name originally came from staff, course number originally came from course, yet I'm able to use the two columns together because now it's just one big happy family. The two columns reside in the rows of that join result. Likewise, salary divided by credit, salary comes from one table, credit comes from the other, but once I've done the join, they're all together. Very interesting, the capabilities that we have here. Very powerful, very expressive. Now, strictly speaking, a join can only be performed against two tables. It's a binary operation. There is no such thing as a 3-table join or an 8-table join or a 20-table join. It doesn't mean you can't do more than one join and bring together that many tables, but it's not done with a single operation. If you look at the underlying theory of relational database, you'll see that join, strictly speaking, involves exactly two tables. It's a binary operation. What we're able to do is we're able to say, let's select from one table, comma, another table, comma, another table, and we can throw a third table into the SQL statement. But if we were to look inside the database as this particular query is being understood and processed by the DBMS, we would actually see that two joins are being performed here. Not a single 3-table join, but a binary join bringing together two of the tables, and yet another join to bring that result table together with the third table. The exact order in which this happens is not important from the standpoint of us looking from a logical perspective. We don't care how it's done as long as we get the right answer. If we were to concern ourselves with performance and efficiency, then the order in which the tables are actually joined could be significant in terms of taking more time or using more resource doing it one way versus another. But that's outside the scope of what we're talking about at the moment. So here, we just content ourselves with saying course, staff, department. I list the tables in any order, and I don't have to worry about the performance or the efficiency. The query optimizer is going to take care of that for me. And if the query optimizer is doing a good job, great. I'll get not only the correct result, but I'll get it minimal resources, minimal amount of time. When we start to see it's taking too long, then we can go and investigate performance. Maybe the query optimizer didn't have enough information, but aside from that, we don't have to worry about it if we're just trying to get the answer from the database. So notice I listed the 3 tables, again, comma separated, and I've listed columns from the course table, from the staff table, from the department table. All 3 tables are contributing columns to the result. I also have a join of course and staff and a join of a row from course with department. Now, here's where it starts to get really interesting. Let's take a look carefully at just what we've got here. What I said to do was take C department, which comes from course, and staff DEPT, and basically I'm saying let's connect these 2 tables here. So there are 2 tables that are joined. Now I got this third table sitting there of department. We already know there's another way to relate department. We could have said that the department's DEPT column is equal to the staff DEPT column and related the 2 in this way. We chose to say let's take department from course and department from department and connect them and relate these tables this way. This connects all 3 tables, but remember we had that alternative choice where we could have connected staff and department instead of course and department. What you have to ask yourself when there's more than one way to relate the tables, does it make a difference which way I connect them? Well, in this case, it's kind of a transitive relationship. So if you say course is equal to staff and course is equal to department, we can conclude that staff is equal to department. So it doesn't really matter which order we list them here. But there are some situations where this will not be the case, that it will be important that we actually list the join conditions in a particular way. Let's go to the database and take a look at a situation where this might come into play. Let's select from department, and let's select from faculty. Okay, when I look at what we have here, if you go back to the introduction to the multi-table operations, you should be quite comfortable with the fact that department and staff are related. And in fact, they are related two different ways. Remember, a faculty member works in or is assigned to a department. So FDEPT is a foreign key making a reference from faculty to the primary key of department. That's a one-to-many relationship. So what we have is FDEPT making a reference to DEPT is a one-to-many relationship, saying that a faculty member is assigned to a department. Okay, but there's a second relationship here. DCHFNO, the department chair faculty number, maps to FNO. So you've got a second relationship. The second relationship works in this way. DCHFNO maps to FNO, and this is a one-to-one relationship, which says that department is chaired by faculty. There's a second relationship. Now, what happens if I take department and I take faculty and put them together in a join condition, and the condition I expressed is FDEPT is equal to DEPT? For each department that exists, how many faculty members will I get? Well, the fact that it's one-to-many says for any given department, I'll get many faculty members if I join them in that way. Well, what if I join them using DCHFNO and I use FNO? Well, if I join them in that way, then for each department, I will get no more than one faculty member, the faculty member who serves as chairperson. This is part of the data semantics once again. Sometimes there's more than one relationship, more than one way to connect two tables. So you have to recognize that when you're connecting the dots here, relating data from one table to data from another table, sometimes there are multiple relationships, and the relationship you choose has to be consistent with the objective of the question that you're trying to have answered by the database. So are we talking about simple employee assignment to a department, or are we talking about an administrative type of assignment? An employee who is the manager, or in this case, the department chair, who's in charge of the department. That's pretty important to understand the possibilities here. So that is, it's possible you could join the tables in either way. They are both correct ways to do a join, but only one of them will be correct given a particular objective, a particular business question that needs to be answered. So if you join them in the one-to-one relationship, but the question really required you join them into one-to-many, yeah, the query will run, you'll produce output, but you're not asking the right question because you didn't understand the semantics here. So it gets a bit tricky here when we start to look at how to join the tables. Sometimes there is more than one way to join them, and it makes a difference how you join them. You could be asking the wrong question. So that's the point that I wanted to make here, kind of related to what we were just talking about here. So sometimes it's pretty straightforward when you relate the tables. Doesn't matter how exactly you do it, it all falls together. But sometimes if you relate the tables and you're using different relationships, it's inconsistent with the objective of the query. You're asking the wrong question. Okay, let's look at another case of joining more than two tables. This one says we're going to join course, class, and registration. A given course may have many scheduled offerings or classes, and a given class may have many registration events involving that class. So I say the course is equal to class is equal to registration. Looks good. Let's go fire this up, get the result, and see what we have. Looks like we're in good shape. We're good to go, right? Well, there's a little bit of a problem here. Again, it comes down to some of the semantics. How is a course related to a class? Well, course is CNO for its primary key. class has CNO for a foreign key. So this relationship is expressed properly. But the unique identifier of a class consists of course number plus section number. It's a composite primary key. And then registration has to have a composite foreign key to capture that relationship between the registration event and the actual class. And again, review the background video if you're not clear on those semantics. So therefore, if I use only part of the foreign key and part of the primary key, I don't quite have the correct answer. This is an almost correct question, or say almost correct question of the database, almost correct query. Take a look at what we have here. And we fire that up, and we got a lot of output, so it's got to be right? I mean, the query ran, it produces output, it's got to be correct. Well, it's not quite right. If you examine the query carefully, you'll notice that student 325, we get the student number from the registration table. This indicates the student involved in the registration event. Student 325 appears in multiple rows. Not a big deal because a given student can register for more than one class. However, what's kind of curious is this particular student registered for two different sections of the same course. Registered for C11 section 01 and registered for C11 section 02. Well, that's not entirely impossible. It's possible that the student said, well, this professor is teaching the section 1 and some other professor is teaching section 2. I've never had either of the professors. I don't know if I'm going to fit into both sections, if it's going to work out. So I'll register for both and then drop the one I don't want. Now that might be the rationale to try to justify this. And you say, okay, that's okay, I could accept that. But a curious thing happens. If you look at the next two rows, student 800 did exactly the same thing. In fact, everyone who registered for section 1 of C11 also registered for section 2. That is going to raise some eyebrows. Something's not quite right there. In fact, the same thing happened down here with T11, which had multiple sections. Everybody who registered for section 1 also registered for section 2. Well, if this is accurate, then that means that there should be 16 rows in the registration table, 16 registration events. Let's see if that's the case. Well, there are only 9 registration events, 9 rows in the registration table, so how could I have 16 registrations? The problem lies back here that this query was almost correct. It wasn't quite right. It missed one little point, and that was the composite key. Class SEC must also be matched with registration SEC. The entire key must come into play. And now, where we saw there were 9 registration events, we get exactly those 9. And look at what happened. No one has actually registered for T11 section 02, whereas in our previous result, we saw everyone registering for it. And that's because we used only the course number and disregarded the section number, the other part of the foreign key, the other part of the primary key. Very important that you understand how tables are related and express those relationships correctly. Composite keys can be a tricky area when you get something that's almost right. And this is especially true in this case when we're dealing with relating more than 2 tables. There could be so much data in the result, and it might not come out quite like it did here, that here's an obvious problem. Here's an obvious problem jumping out at us. But if there's so much data in the result, plus an order bias thrown in, it might mask the fact that we didn't ask the correct question. We didn't join the tables properly. So it's something you want to be very attentive to. Okay, we already looked at the idea of producing a cross join or a Cartesian join, Cartesian product or cross product. We did that with comma-separated join by simply omitting a join condition. We didn't actually run it, but the idea is we discussed it in practice or in theory. Well, because it's part of the relational framework or the theory for relational database, it has been formally implemented as an actual operation within SQL. So you can actually say select from one table, cross-join another table. It's redundant because we could get this by simply saying select from one table, comma, another table, and omit a where clause that includes a join condition, and we produce the cross-join. So we don't really need it, but it's here as part of the SQL syntax. And here are a couple of examples, and I'll leave it for you as kind of an exercise or a curiosity if you really want to see how it works, to go ahead and try it out behind the scenes. Well, there's one other join that we do want to take a quick look at, much more, I think, from a theoretical standpoint than a practical standpoint. Something called the natural join. The concept of the natural join is quite nice and practical, but the way it's implemented is such that it may not be all that useful to you. And bear with me as I explain just what I mean here. So we would say select from one table, natural join another table, and optionally have where clause conditions. Notice we could run this query here. Let's go ahead and try this one out, and then we'll discuss this in more detail. So here's the natural join. And what do we get? We get 9 rows. Let's clean this up a little bit here. Instead of getting all of the columns, let's say that what we want to do is pick a subset of the columns. So perhaps what we're going to do is say, let's modify this, and what we'll do is we'll get things like the course description, and we'll get the course name, we'll get the lab fee, we'll get the credit, we'll get the day of the class, and the time of the class, and the room of the class, just to pick a subset of columns here. And it's a little easier to see. Now, what's interesting is if we look at this, what we're seeing is information about the different courses, the different sections of the course, and so forth. And notice it's not a cross join because we have 9 rows. What does that mean? In the course table, there are 14 rows. And in the class table, there are 9 rows. Each class is joined with exactly one course, and we get 9 rows because there are 9 children. We don't get all of the parents, but we get all of the children. So it makes sense. So this is a natural join. How did it work? The way it worked is the 2 tables, if you describe them, share a column name of CNO. What it actually did was the natural join is an inner Equi-Join from the course table where CNO from course is equal to CNO from class. Let me show you how it works here. You see these 9 rows. Let me take this query and do a little bit of a modification to it. What I'm going to do is say I'm going to go from course and class where course.cno is equal to class.cno. And I get the same 9 rows. So it's an inner Equi-Join, but notice we didn't have to express this condition. And if we go back and look at what we had here, we see here are the 9 rows from the natural join. And what we have here are the 9 rows from my inner Equi-Join. So what's the difference? Obviously, we didn't have to type the relationship, but here's what happens. Let's go and do this query now. And I'm going to say, give me all of the columns. And watch what happens. Now, it's kind of cluttered on the screen here, but we want to look at this. Notice that we said the course CNO is equal to the class CNO. And what we have is CNO appearing 2 times because we said select asterisk, give me all of the columns. But each time you see CNO appearing in the course columns, the value for CNO that appears in the class columns is identical, because that's what we asked for. It's equal. So we're showing the same column value 2 times because it's equality. It's an Equi-Join. It would be more natural to show that value only 1 time, right? That's what the natural join is. So when we say let's do the natural join, of these two, we don't have to express the relationship. And what we get is CNO appears once here, and if we scroll over, we don't see a second instance of CNO. It doesn't appear. It's shown only once, because it's more natural to show that column only 1 time rather than twice, because it has the same value in both instances. That's what the natural join is. So you might get excited and say, well, that's pretty neat. Why do you think this is not that practical? Well, here's the reason it's not practical. How did it decide to make the join condition kind of implicitly this condition right here? Course CNO is equal to class CNO. How did the system decide to do that? Well, you might say, well, it's that metadata with the referential integrity that you've been talking about. Foreign key equal to primary key. Well, that's a good guess. That seems logical. But that's not the basis for the join here. Take a look at another example. Let's describe the class table, and let's describe the registration table. These 2 tables we know are related, right? You've got the primary key of class, and you've got the foreign key of registration, and that's how they would be related. Well, it turns out if you have multiple columns, this will work here as well. And again, you might say, well, it looks like primary key, foreign key, the referential integrity again. And we get the 9 rows, and it looks great. But there are 2 other tables that we want to take a close look at. Let's look at the department table. And let's look at the student table. These 2 tables are related, right? A given student majors in a particular department. That's how we've captured that notion in our database. And a given department will have many students who major in that department. So the primary key here is DEPT in department, and the foreign key is SMAJ in student. If it's based entirely on referential integrity, then the system should pick up on this point. Let's see if that's the case. So we're going to select from department, natural join, student. We get 16 rows. Well, it looks pretty good, except notice the same student appears multiple times. There are only 4 students, and there are 4 departments. 4 rows in one table, 4 in the other. This is actually a cross product. We have 16 rows. Because notice curly here is paired with every department. But he's only majoring in one of them. He's not that bright a guy that he's a quadruple major. He only majors in one department. He's not majoring in 4 departments at once. In fact, everybody here is majoring in all 4 departments. What has happened is the condition here says, let me go against the department table and look if there are any column names that are identical, in the other table. And it doesn't find them. It doesn't look at the metadata where it's looking at referential integrity, primary key and foreign key. If it did that, this would be great. But the natural join is based entirely upon columns having the same name in the 2 tables. It's that simple. So if I had a column called X in the department table, and I had a column called X in the student table, and they were completely different types of values, and I say let's do a natural join, the system would attempt to say where department.x is equal to student.x. Even if they don't contain the same type of data, it might attempt to do that. So the point is the natural join is only going to work in relational database systems if the database tables have been designed such that the names of the columns in one table and the names of columns in the other table happen to match, if the names happen to agree for, say, foreign key and primary key. Otherwise, if there are no columns that match, it will revert to being a cross join or Cartesian join, which is not going to be helpful to you. And if there are columns that match for referential integrity, those don't come into play at all unless the column names are the same. If there are columns that match based on name and they're completely different types of data, the system will attempt to use the values in those columns to do the natural join. So while theoretically it's interesting, in practice it may not be that useful if the tables have not been designed with this idea in mind of having common column names. So that's why I say it may not be that practical. There are many real-world databases that I've seen for which this would not work because the column names don't agree. Okay, so a couple more examples. This is an inner Equi-Join, but this is the same idea using the comma separated as we would get by doing a natural join of these two tables without having to express any join condition. It would look at the column names that are common and match them. So if there's one column or 5 columns that are the same, it will match all of the columns with the same name. Okay, and then class and registration. We could also have a filter condition here. No need to express the join condition if the tables are set up with the names being the same. And then finally, that brings us to the next category of join, which we call the condition join. While a natural join is based on columns that have the same name and presumably the same semantics within two tables, we have the ability to kind of take it a step further and specify specifically which column or columns we wish to use from two tables to express a relationship or join condition. And this is where the syntax for the condition join comes into play. So a condition join is formed again by using the join keyword to separate the two tables. Rather than comma separated, we're using the join operator. And we also have grouped or connected to the join is an on clause. And the on clause is where we express the condition or the relationship that is going to be used to perform the join operation. So that's why they call this a condition join. We're expressing the condition explicitly. A little bit different than a natural join. We can also have filter conditions. Generally, I believe it's a good idea to restrict the use of the on clause to identify the join condition and use the where clause to do the filter conditions. It's possible when you're doing an inner join to put everything into the on clause, and that will not change the behavior. But you want to take great care in getting into a habit like that, that you don't do that with an outer join. Later on when we talk about outer joins, depending upon where you put your filter condition, whether it's in the on clause or the where clause, that will affect the timing as to when the condition is evaluated when you're doing an outer join. But with an inner join, it's really not a big deal. But I prefer to be consistent and to be clean about this and to put the filter conditions in the where clause, separating them from the join condition or join conditions. So here's an example. We're saying select some columns from the course table, and we're taking course join class, and this is how we're going to do the join. The course number CNO, the course number coming from the class table, a CNO from the class table, and then these are the filter conditions. If we were to do this using the previous technique that we discussed, the comma separated join, we can do exactly the same in terms of asking a question of the database and get the exact same result, but the syntax is a little bit different. course, comma, class, and then notice the where clause does two jobs. It introduces both the filter condition and the join condition. This is why I don't think it's preferable to just put everything into one clause. Take advantage of the fact that the on clause really could do the job of servicing your condition, and the where clause will handle the filter condition. In that case, it makes the query somewhat self-documented. Now, let's go a step further and see how this works in action. Okay, so here's the condition join, course and class being joined, and the on clause expresses that join condition or relationship, and the where clause expresses the filter conditions. Fire that up, and here's what we get. Discrete math and hedonism. Here's the comma-separated version of the query. Two tables, and the where clause then introduces the join and the filter conditions. We run the query. We produce the same result. So there's no difference in terms of functionality that's being introduced by altering the syntax here with the condition join. It's just a different way of phrasing it. Sometimes people find it easier to understand the condition join than the comma separated. Just an alternative way of expressing the question. So when forming a condition join, the join condition has to be specified in the on clause. If you say, well, this is pretty exciting, I'm going to try this new syntax, new because we started with comma separated and now we're learning the condition join. So you do the join keyword instead of a comma. But force of habit, from what I've shown you previously, you jump right into a where clause. This will cause a syntax error. And you'll get a syntax error whether you're using Oracle or SQL Server. The databases simply say that when you have the join keyword, you must have an on clause before you can do anything else. And the purpose or the function of the on clause is to express the join condition or relationship. So it's mandatory or obligatory that you have the on clause prior to doing anything else. One other thing to take a look at here is we have talked about correlation names or correlation variables or table aliases. And we had indicated that you could introduce those immediately after the name of the table, put your little identifier, whatever it's going to be. And I say little because typically it's abbreviated. It's much shorter than a table name. So you put that identifier, and then you put your table and another identifier and so forth. And then those identifiers or labels can then be used anywhere throughout your query to qualify the names of the columns. Well, even though we're changing syntax here and using the condition join with the join keyword and on, we're still able to use the table aliases or correlation variables. So that's a real nice feature. We can take it a step further here and say, well, suppose I'm going to join class and registration. Some of you may have been thinking about this already, that we have a composite primary key, a composite foreign key. Well, the on clause will accommodate you here by allowing you to express multiple conditions and using a Boolean connector such as AND. So we're saying I'm going to join class, which consists of CNO and SEC for its unique identifier, with registration, which consists likewise of CNO and SEC for its foreign key, and we want both CNO to be equal and SEC to be equal from the different tables. So we use AND to combine the two simple conditions, and we put this complex condition in the on clause, similar to what we've done for complex predicates for single table operations in a where clause. So we're doing that quite naturally here. So we also can use the correlation variables, as we saw here, to qualify the columns for the join condition. We can also have a filter condition added after we've completed the on clause to express the join condition, and then use the correlation variables to do the qualification. Sometimes people might like to do a more kind of visual grouping to kind of emphasize that it's a combination of course number being equal and section number being equal that constitutes the condition for the join. So we can put parentheses in here to make it a little bit more of a visual aid to kind of draw attention to the fact that there are composite keys involved. We can also take it one step further and note that I'm joining class and registration, and then I also want to join student. All I do is say join and put the on clause. Then I want to do another join. This makes it a little more obvious that it is a binary operation. I do another join and introduce another table. This table has to be related to something that I've already looked at. So can I relate student to class? Well, not directly. There's no way to do that. Can I relate student to registration? Yeah, I can do that because a registration row reflects an event for registration, which includes class identification and student identification. So I'm then going to join student to R, which is registration.sno, equal S, which I've given is my alias for student.sno. And if I add another table, I could say join this other table on, and then relate it to any of the three tables that I've already seen. Although this seems like I'm introducing some kind of a procedure or a process, step by step, do the join in this particular order, that's not what the system is going to do. The system is intelligent enough with its query optimizer to make a determination that, well, even though you said to join the tables, I'm not going to join them in the order that you've introduced them in the query, because looking at cost-based query optimization, it makes more sense to do the join in a different order. I'm simply expressing logical relationships here. There's one other type of join we want to take a quick look at, and that's inner join. But the thing about this is everything we've been talking about up to this point has actually been an inner join. We've just not made a big deal about it. We've not been explicit about it. The inner join is introduced by having the join operator actually extended to be inner join, and then we express what the condition is. Me, I don't personally like this because you can see I've made a lot of typos, and that's one more word I have to type, one more chance for me to make a mistake. But some people really like the idea of kind of self-documentation in the query and adding the word inner. I've seen this used a lot in practice, particularly with SQL Server databases. People will do outer joins and inner joins, and then they just simply make it explicit that it's an inner join. Not really necessary, because if you omit the word inner, you get an inner join anyway. And let me show you what I mean by that. Go into the database, and here what I'm going to do is get my join of staff and department, and this is an inner join. And let me take the query and make a slight modification to it. I'm simply going to omit the word inner and just say do a join. And I get the same exact result. And you can take a quick look at that and confirm. Same result. One had said inner join, made it explicit, and the other simply said join. But the same condition was expressed in the on clause. And again, inner join and join, didn't make it explicit and say inner join. That's what it defaults to. That's the behavior. So we really don't need the operator. Again, it's a little bit more redundancy introduced to the language. Some people like it. I'm not going to criticize it. For me, I don't particularly use it because, as I said, it's more to type. It introduces another opportunity for me to make a typing mistake. And I can make enough of those without any help. Okay, let's summarize what we've talked about. We've covered a lot in this section, and we've pretty much exhausted the idea of the inner join. It's a tad more that I'll hold in the background. When I talk about outer join, I'll throw a little bit more at you. That's kind of interesting. So the join operation is a multi-table operation that effectively combines rows from two tables. I express this at the idea of a concatenation of rows, appending the columns from one row to the columns from another row. So we basically made a result table with these kind of extended or elongated rows, the concept of concatenation. The join condition expresses a relationship between rows in a table, and this relationship does not have to be one formally defined to the database, such as primary key, foreign key relationship. It can be any connection you want to make. You could actually draw a connection between, say, department budget, which is a numeric field, and employee foot size, which is a numeric field. If there was some reason to do that, the system would allow you to do that. But obviously, there's no such relationship defined, at least in my database. Okay. An inner join returns all rows that satisfy the join condition, but again, it's not necessarily every row in a table, only the rows which satisfy or meet that join condition. There are different ways to express a join. Again, alternative syntax. We looked at comma separated and also condition join. We said the real difference here is simply syntax. You're not getting any different functionality or behavior. That will be a little bit different later on when we talk about the idea of outer join. A natural join was a special variation of an Equi-Join. Again, I kind of downplayed this because I don't see a great deal of value to it, because the database must be explicitly designed to accommodate the natural join operation by having column names be the same in the two tables. The concept of a natural join makes sense, but the implementation of the operation is not necessarily practical. Finally, there was a cross join. It did not include a join condition, and it produced what was called the Cartesian product or the cross product. Each row in one table is concatenated with every row from the other table, producing a massive result, much of which may not have any real benefit to you. So, I have a website, timhartley.com, where you can go and look for the menu that says Insightful Professor. There's a link there, and you can download the file called Inner Join, which will have all of the queries that I used and some more that I did not run. So if you want to try any of these out without typing them in, feel free to grab that. And again, there are other files there. If you've been watching the other videos, you're aware of what's there. So hope you enjoyed what we presented, found it useful and informative. And if you did, click on the little owl icon to subscribe to the channel. That'd be great. We'd appreciate that. A little bit of recognition, kind of a pat in the back that we're meeting with your approval. And once again, thanks for watching.